Hello everyone, I'm Javier Martin from Team Noisy Students, and I'm going to present to you our solution to Riiid's answer correctness prediction competition organized by Kaggle, which ranked number 3. I'm going to start with some background about us. I studied computer science, and I'm currently working as a computer science teacher in Torrevieja, a small town in the southeast of Spain. My teammate, Andres, he's a telecommunications engineer and the founder of several companies. We both have some background on previous competitions, both traditional programming and deep learning. Here's the basic diagram of our solution. As you already know, the problem we were trying to solve was to predict whether a student is going to answer a question correctly or not, based on historic data of previous answers of about 400,000 students. The questions were specific to an English learning application created by Riiid, and we were provided with rich data such as the type of question, up to 6 tags, the time it took the student to answer the question, and whether the question had some feedback explanation, among others. We created new features derived from the given ones, as I will explain in a minute. We have 3 big groups of features: those that can be encoded categorically, such as the question ID or the type of lecture. We used an embeddings layer followed by a linear layer for those. The second block is continuous variable. We simply concatenated them together and put them through a linear layer. For the tags, we used an embeddings bag followed by another linear layer. The results of all linear projections were added together and put through the transformer, followed by a linear layer and softmax layer to get the final predictions. We use the traditional transformer with a number of encoder layers and the same number of decoder layers. We feed the transformer's encoder input with both question and answer related features, shifted one position to the right. Also, we hide all answer related features such as answer correctly, user answer, or whether the question had explanation from the decoder. We trained 2 transformers for our final solution. One had 3 encoder layers and 3 decoder layers with ReLU activations, and the other was 4 plus 4 layers with GeLU activations. Both models' dimension was 512. We don't have a proper ablation study, as during the competition we focused on staying competitive, but we did notice big improvements when we added 3 specific features. The first one is question elapsed time, which I abbreviated here as QET. The QET value was given to us delayed 1 question, or 1 questions container to be more specific. To be able to use QET as a feature, we simply shifted them 1 container upwards. The second important feature was the time since last interaction, or TSLI, which is the timestamp of the previous question subtracted from the timestamp of the current question. The third one was the number of attempts a particular question was asked to a user. This feature was very useful because around 11% of the questions were repeated questions, and the student was more likely to answer correctly to those as opposed to questions that were asked for the first time. We use Jupyter, Visual Studio Code, PyTorch, and Fast AI as our main development tools. Our solution takes between 4 and 5 hours to train on 6 RTX 3090 GPUs. Here's a detailed description of our feature engineering. I already talked about QET and TSLI and the number of attempts per question. QHE means whether the question had an explanation, and we shifted it upwards 1 container, the same way we did with question elapsed time. The TSLI, or timestamp delta, could be a big number if the user abandoned the application for a few days or even months between 2 consecutive questions. So we decided to clip TSLI to 20 minutes and include it as a separate feature. We also thought it would be valuable to add the timestamp modulus 1 day and modulus 1 week as features. The rationale between this is that perhaps a student performs better in the evenings or is more concentrated on Saturdays, for example. We also provide the network with the probability of occurrence of each question and the ordinal place of the question within the container. For the training phase, we use the constant learning rate for the first half of the training, followed by a cosine decay during the second half. We used the default 0.1 probability dropout in PyTorch, and we tried Adam, lamb, lookahead plus radam, and lookahead plus lamb as optimizers. We had a maximum limit of 9 hours allocated for inference on Kaggle server. So during inference, we did a time-based adaptive ensembling of two models. In practice, what this means is that the inference loop will try to use two models as much as it can, but it will drop one of the models if it sees that the ETA extends beyond the allocated 9 hours. I'm going to explain two strategies that I think set us apart from other competitors. First, as opposed to previous state-of-the-art solutions such as Saint Plus by Riiid, we decided to swap the encoder and decoder inputs. This means putting both question and answer related data in the encoder, whereas the decoder only sees the question related data. Our intuition behind this lies on the cross-attention value path from the encoder to the decoder. We think that the single most important feature the transformer relies on to predict the future performance of a student is their past performance. So we wanted the encoder-decoder attention to ask itself the following question. Hey, I'm a question about grammar. That would be the query. Let's match other grammar questions in history. That would be the key. And let's focus the attention on how the user did on those questions, which is the value coming from the encoder. Our second strategy was to include all features in both the encoder and the decoder, with the exception that the answer-related features were hidden from the decoder. We thought, why restrict the inputs to the transformer when the transformer can choose what's useful and what not by itself? This allows both encoders and decoders self-attention to establish richer relationships between data. We also think the timestamp modulus features were novel. Also, we were able to cram the number of times a question was asked to each user and the number of correct answers in Kaggle's limited space, and this was very challenging because the two matrices used about 12 gigabytes of RAM. The fact that we shifted the question elapsed time and question ahead explanation features to their corresponding containers was also very useful. We also used T-fixup initialization technique that allowed us to remove all layer normalization layers and the initial warm-up of the learning rate. Having 6 GPUs available wasn't critical to achieve a better score, but it was very helpful to run more experiments. Kaggle required us to send the source code for evaluation on a hidden test set. To prevent information leaks from the hidden set, which could be exploited by competitors, Kaggle decided to provide no information whatsoever in the event that the inference script failed. So error diagnosing and debugging was really hard in this competition. Finally, the fact that we shifted the question ahead explanation and question elapsed time features one container to the past brought up the following problem. When inferring a question that belongs to a container, QET and QHE attributes of questions belonging to the same container are not known until the following container is revealed. So this should be masked in the same way future questions are masked. This means that none of the questions entering the encoder and belonging to a container except the last one can attend to any of the questions in the same container. We do allow the last question to attend the other questions, because as the encoder input is shifted to the right, by the time the encoder sees the last question in the container, it means that the next one from a different container has entered the decoder, and the answer related information to the previous container has already been revealed. Thank you for your attention. For more information, please refer to our paper and the source code which we made available on GitHub.